Hey, grade nines. So in today's lesson, we're going to go over linear versus nonlinear relations. So specifically comparing the two of them. And then we're just going to be talking specifically about nonlinear relations and what that means. So let's just get started. So linear relations, we already talked about this a little bit. So graphically, we know that they're going to have a straight line and the slope is going to be constant. So a reminder, we talked about slope a couple times. So the fact that I brought it up a few different times in different lessons in different ways probably means it's extremely important. So make sure you know what this word means. I would say if there's anything in grade 9 that you take away, if there was one big concept, it would be slope. Make sure you understand what that means, right? So slope means the rate at which it's increasing or decreasing, right? So obviously in a straight line, we can see that I could take any 2 points, and if I were to calculate how much it's increasing by, how much the y coordinate is increasing by relative to the x, so this is a change in the y and this is a change in the x, it should be the same no matter what, right? So it's going to be the same proportion regardless. So I could take these 2 points over here, and while they might look, it might look like it's different, it might be a different slope because they're closer to each other, it's still the same ratio if you compare the change in the y and the change in the x here. So what we notice is that the slope, which is change in y, and remember we use the symbol for change in y, over change in x, it's going to be the same throughout the whole line. The other important point is that the first differences are all the same. So if we're looking at a table of values and then we calculate what the difference between the y values are when the x's are also changing by the same amount, so we need to make sure that the x's are constant, then we'll notice that the first differences are the same, right? So they all increase by the same amount. So on a table of values, you might have, and I'm just making this example up, and I know we talked about this already, but I figured this is a good time to review. Okay, so let's say I have a small table of values like this, right? So what I mean by the first differences being the same is that you'll notice some sort of pattern, right? Like 4, 7, 10, and 13. And I think everyone can kind of see here, we're increasing by 3 each time. So that's what the first difference is. The 3 right here is our first difference. And we calculate that by taking the y value we have minus the y value before it. And the last thing, and this might be a little bit new, we did talk about this in Unit 2, but we haven't gone back to it. The degree of the equation is 1. So degree, just sort of a little reminder, is the highest exponent that you see in an expression, right? So the highest exponent would be 1 in this case. So in linear relations, the highest degree is 1. What are nonlinear relations? Well, this is pretty easy. Nonlinear basically means any relation that's not linear. And that could be, it really could be anything, right? It could be a curve. A lot of times we talk about curves. Could be, it could be something later on you're going to learn about exponential functions. It could even look something like this. You're going to learn about that in grade 11, grade 12. So trigonometric functions. I don't want to get into that for now, but essentially it's anything that does not have a straight line. Okay. And then also we talk about circles. You're going to talk more about that next year. That's another example of a relation that is nonlinear. So basically, if it's nonlinear, then it doesn't have a straight line, it doesn't have a constant first difference, and it doesn't have a degree of 1. If any of these conditions are met, then you know it's going to be nonlinear, right? So that's kind of the main condition that we see there. Okay, so if it's linear, so let's just see, is it linear or nonlinear? So we're just basically checking, does it meet any of these, does it meet all 3 of these requirements, right? Because it has to meet all 3 of those requirements there, or does it not, right? And then we can decide afterwards. So is it linear or nonlinear? Well, let's see here. It's not a straight line, so we know that this is actually something called a parabola. You're going to learn about that in grade 10. So because it's not a straight line, then obviously we know that it's not going to be linear, so non-linear. What about this one? Well, this is a straight line. So because the graph has a straight line, we know it's going to be linear. There we go. Is this linear or non-linear? Well, it is a curve, so we know it is going to be non-linear, right? Because it should be a straight line. Is this linear or non-linear? Well, let's check it out. But we can calculate the first difference simply by subtracting off the y values, and we first double check that the x values are all increasing by the same amount. Are they all increasing by the same amount? Absolutely, right? We can see here that we're adding 1 each time in between them. So this is all the x values are increasing by the same amount. So we know that we can quickly do a check here to see it for the y values. You can simply find the first differences to compare. So we're going to do 8 minus 5 first, and let's figure out what that gives us. That gives us 3. Then we do 12 minus 8. That gives us 4. 17 minus 12, that gives us 5. And finally, 23 minus 17, that gives us 6. So what do I notice? Here are my first differences. Are they the same? No, they're not the same, right? So if the first differences are not the same, then it's pretty clear that it's not going to be linear, right? It has to meet that condition, right? So the first differences should have been the same in that case. So when we're looking at our criteria, whether it's linear or nonlinear, it just depends on what's given to us, right? So the whole idea here is that if you're given a graph, you would be checking to see if it's a straight line or not. If you're given a table, then you're checking to see if the first difference is constant or not. So this is where you're going to be checking for table values. And then the last thing is if you're given an equation, then you check for the degree, right? So hopefully that kind of makes sense there. So I'm just going to go back to this last example we did. So we have two more here. Okay, so in this next one, we're given a table of values, and then we are asked if it's linear or nonlinear. Now, you could follow the same steps as before, but there's one big difference. Do you notice anything a little bit odd about the x coordinates? So you might notice that the difference between them is actually not constant in this case. It's going up by 2 here, then it's going up by 1, and then it's going up by 3. So it's really not consistent at all. So because the actual x values are not increasing or decreasing by the same amount, and they're not being consistent, it's not a constant change there, we need to be really, really careful because we can't just subtract. It's not as easy to just subtract off the y values. And this is where people kind of get stomped, right? And then I'm purposely trying to trick you a little bit with this one. You gotta really analyze it, right? So if I did the first difference, I just want to show you what would happen if I find the first difference. It's 6, then 13 minus 10 is 3. And finally, oops, that's the 3 there. 22 minus 13 is 9. So looking at this, it wouldn't look like it's linear, right? Because the first differences should all be the same, and they're not. So that's already making me kind of second guess what's happening here. So it makes me think that it's not linear. So we got to be careful with this. It definitely doesn't look linear, but if it's not a constant, if the x's are not going up by the same amount each time, then what we're going to have to do is actually use the idea of rate of change that we learned about yesterday. So what we learned about yesterday, we talked about how obviously slope is ideal when you're given a graph, right? You just find the change in the y, change in x. You find the first difference for table of values, but if the change is not consistent, if the change between the x values is not constant, then what we want to do is you want to pick any 2 points. Doesn't even matter which 2 points I pick. I'm going to pick the first 2 just because those are a little bit easier for me to work with. And all I'm going to do is I'm going to pick those 2 points and calculate the slope. So I'm actually going to do this down here so you can see how I'm doing this step by step. So I'm going to pick 2 and 4 and 4 and 10. And just a little reminder, I know some of you have asked me about this. I'm not sure how comfortable you feel with coordinates, but when we are talking about coordinate pairs, the x always comes first, okay? So it's 2 and 4 and 4 and 10. So what we're going to do in this case is we're simply going to calculate the slope, the rate of change, and that is the same thing as slope. So I'm just going to write slope, rate of change. So I need to know it's the same idea here. And what I'm going to do is I am simply going to find out what the difference in the y is. And I'm going to divide by the difference in the x. By the way, sometimes I use difference in y over difference in x, and sometimes I use change in y over change in x. It's the exact same idea, okay? And sometimes in math, just to make things easy, we like to use symbols. So you might see this a lot more instead of actually writing out the words. So what I'm going to do is I'm just going to find out how much the y has gone up by, and then how much the x has gone up by. So for the y, let's start with that first. I can clearly see here that between the 4 and the 10, I am going up by 6. Hope that kind of makes sense, right? And what I could also do as well is I could simply take 10, which is this y coordinate right here, and I subtract off this y coordinate right here. And again, it's all about being consistent. You could do the other way. You could do 4 minus 10. But if we decide to go in that direction, then we have to do 2 minus 4, right? So just kind of keep that in mind. So I'm doing 10 minus 4. And then when I find the difference in the x, I go back here. And actually, I noticed that I already found the difference in the x. The difference in the x for these two was 2. And I'm just going to show the work for that. And I'm going to show it a little bit differently. So for the x, I do 4. I'm going to circle the 4 and the 2. So all I'm going to do is take 4 minus 2. 4 minus 2 right there. And then my next step here is to simply calculate what this gives me. So 10 minus 4 is 6. And 4 minus 2 is 2. And that means that my slope is 3. So that's how I calculate the slope there. And what you can see here is that even though it might not make, if you look at this and you're thinking, well, this like how do I know that the slope is the same for all of them? Well, you can simply calculate that this change of this constant change of 3 for every single x value would work throughout. So let's actually test it out. So we know that if we have, so I'm just going to erase this so you can actually see it here. If I were to, it's almost better if we extend this table. And I have 2, I know there's supposed to be a number missing there, 3, 4, 5, 6, 7, and finally 8. I ran out of space there. So what I'm going to notice is that my the y value that corresponds to 2 is going to be 4. I know that the slope should be 3, so I know that this one's going to be 7 right there. This is going to be 10. So this is already starting to make a little bit more sense, right? I could notice that it's going to be linear. I'm just adding 3 consistently. And what would come right after that? It would be 13. And that makes sense because I have 13 right there. And then the next one is going to be 16. Then we have 19. And finally, the y coordinate that corresponds to x equal to 8 would be 22. And this should all make sense because we're simply adding 3 every single time. So because we are adding 3 by 3 every single time, we have a constant first difference, and this must be linear. So this is a bit of a tricky one, and I did that on purpose just to kind of throw you off a little bit and good practice with finding slope there. So this one, it didn't seem like it was linear because if you, like I said, if you find the first difference alone, you notice they're not all the same. But you should dig deep into the pattern and always check that the change in the x is consistent as well. Just so you know, I don't think I'll give you a lot of those questions. If anything, I might give you maybe one at most. But I just kind of want you to be aware of those little exceptions that come up, okay? So obviously this one is linear, a bit of a tricky one, right? And another thing you could do as well, and I mentioned this already, is use technology to your advantage. Use a graph paper to your advantage. If you want to check if something's linear, we absolutely could look at table values and find the first difference. But you have another option. Put this on a graph, right? If you put this on a graph and then you draw a line going through it, and you notice that the line is perfectly straight, then it's linear, right? That's another way to check that this is correct. And one last one here. Is this linear or nonlinear? This one also looks a bit strange. So it doesn't look like a typical equation we've seen. And most of the time when we've seen equations, we have seen them in this form. Y is equal to mx plus b. So this is kind of the form that we're starting to see. And we are going to talk about this in the next lesson. So this will be much more important later on. But we already start noticing that it doesn't really follow this pattern. But we always look at this and say, all right, well, what's the highest exponent? Well, I can clearly see here that the highest exponent is a 1, right? This has exponent 1. Sorry, this has an exponent of 1, exponent of 1. So the degree here would just be 1. So this is still linear. And that last one, just so you know, is a little bit trickier. I don't think I'd ever give you anything too tough like that. But if you have an equation like this, and again, you're not gonna learn about this until grade 10. But if you have something like 2x squared, or y is equal to 4x cubed, or whatever it may be, these are clearly not linear because the degree or the exponent right here you can see is not 1. right? So the highest exponent must be 1. Okay, so there's a homework. And again, for this one, you're going to notice that a couple of the questions are going to ask you to use technology to help you out. So a lot of this is, like I said, the ones with the E are extra work. So there's a lot of extra work on here in this one. But I think this is a great way to start learning just how Desmos works and how to actually graph these out. I just want to show you really, really briefly how to graph out relations that are not linear, because we haven't talked about that. So let's say I go, I'm just going to open this up. Let's say I go to Desmos and I want to graph out, I'm just going to write the equation I want to maybe graph out. So let's say that, oops, just trying to get the pen open here. Let's say that your equation is 3x squared. I think one of them is 3x squared in the homework there. So how would I actually graph this out? So what I'm going to do is I am simply going to write out y is equal to, and I mentioned this already, you have to put an equal sign there, and then you write 3x. And now if you want to get a square, it depends whether you're using your laptop or your phone. If you're using a laptop, you can use the little arrow pointing up, so the upwards arrow, to create an exponent. So if I do that, it automatically creates this exponent like this for me, and it basically creates it allows me to write in the exponent there. So I can type in the exponent 2, and then I have the graph. Now, if you're using your phone, so I want to show you a different thing you're going to be using here. If you want to square something, you can actually just click on this button that says a squared. Click on that, and it automatically creates the graph there for you. So that's what that graph is supposed to look like for the graph for this equation here. So you can see, obviously, this is a little bit funky. You're going to learn a lot more about this in grade 10. But just want to make you aware of how to use technology, because you sometimes will need to do that to kind of help you visualize it. And also, if you're doing coordinates, I know some of you had asked about that. How do you do coordinates? Let's say it's coordinates 1 and 3. You have to type in the brackets there, okay? Really key point. And I will take off marks for sure on this, right? And it seems like a very picky thing, but it's absolutely necessary. When you are doing coordinates, you have to put the brackets around the points, the x and the y coordinates. Extremely important. If you don't put brackets around it, doesn't really mean anything, right? You have to specify that we're looking at coordinates there. So to do the coordinates, you just type in the x and y coordinates and brackets, and that's it.